Alright, so let's start up on the second part of today's class. So what we're going to do now is we're moving on from Chapter 4, taking those skills that we've developed, in reality taking all the skills that we've actually been developing this whole time, and we are finally now going to get into hypothesis testing. We're finally now going to get into the procedure that we use to go from scores with a sample to saying something about an entire population. That is what the goal of hypothesis testing is. And this is where all the hard work is going to pay off. So all that time we spent working on means and standard deviations, all that time that we spent working on z-scores and a normal distribution curve, all that practice that we did in terms of all the assignments, the pre-test and post-test, also that you can get very familiar, very quick and agile with these ideas, are going to pay off now because we're going to put them all together into this hypothesis testing procedure. So we're finally at that point where we can take a look at actual data, we can take a look at actual psychology situations and make generalizations about a population, determine if a treatment is effective, and the skills that you're going to learn starting now are going to be the skills that you will yourself use in any sort of hypothesis testing that you ever do. So for example, if you're a psychology major, for your advanced lab, you may very well use one of the procedures that we're going to learn in the remainder of this course. So we're starting the cool stuff, so let's get right down to it, and we'll start off with an example. So let's say that there's an elementary school, and this elementary school notices that their students are falling behind. Their students are not doing very well academically. And one of the things that they suspect is that maybe their students are suffering from low self-esteem. So they might call you, let's say that you graduate and become a developmental psychologist, they might call you in and they might say, you know what, take a look at our school program, take a look at our school day, and see if you can do anything to help these kids reach their academic goals. See if you can do anything to increase the self-esteem of our students. So let's say that you go there and you start doing an analysis of their program, and you notice that they have a very traditional physical education program. A program that is based on drills, based on doing just endless push-ups. And you think that this might be the cause of lower self-esteem for some of these children. So what you do is you implement a games program for their physical education class. So instead of just doing endless drills, they participate in a games program where their physical activity is tied directly into playing a game. And you want to know by the end of this treatment program, by the end of this games program, do your students have higher self-esteem than the general population of American students? So you want to know if your treatment has raised the self-esteem of your students to a level where they are now higher in self-esteem than the general population. And the challenge that we're going to see is even if your students do have higher scores of self-esteem than the population, even if they rank higher than the population, we need to decide why do they rank higher. And there's two possibilities. One is that your program actually works, right? One is that your program actually works. This game program is a great way to do physical education while at the same time raising the self-esteem of the students. In that case, you would want to get on the phone and you would want to tell everybody about this wonderful games program that you have, call every single school that you know of, and get them to put their children on this games program. That's possibility number one. Your games program actually works. Possibility number two is that you got a fluky sample. So we know, because humans are diverse, that even in a school where on average students are low in their self-esteem, we might, just by chance, have picked students that are high in self-esteem, right? So if this is the distribution of self-esteem in that school, and on average, right, the self-esteem mean is lower for the school on average, we still had to pick a sample from this school, and maybe we picked students that were just higher in self-esteem to begin with. So maybe our program does nothing, and we just got lucky and chose students with high self-esteem. So before we start generalizing to the population of students, we have to decide which one of those situations is it. Does our program actually work, or did we get an unlikely sample? All right, and we need to know that before we can intelligently generalize or not generalize, as the case may be. All right, so the outline, what we're going to do, we're going to go through the core logic of hypothesis testing, the core idea that underlines it all. And then we're going to go through the 5-step hypothesis testing procedure that gives you the ability to make that determination. All right, so the core logic of hypothesis testing. So hypothesis testing, this is a systematic procedure that allows us to take a look at a sample and see if it applies to a hypothesis about the population. So we might have an idea about a population, like this physical education program will work for the population. That's a hypothesis, that's an idea. And we test it by taking a look at the sample and seeing if we can generalize to that population. So this is, again, going from a distribution, a sample distribution of scores that you have access to, and being able to generalize about something about the population. So that's the first thing to keep in mind. We always want to say something about the population. We're always trying to say something about the population. You don't need inferential statistics to say something about your sample. You can just look at your sample. But in order to say something about the population, we need ability to generalize to see if our research supports a hypothesis. And again, this is a systematic procedure. And that is required because we as human beings, with our human minds, are horrible at going from a sample to a population, at generalizing from a sample to a population. We tend to see what we want to see, and whether or not that's the truth, we're oftentimes blind to it. So thank goodness we have this systematic procedure where we can remove all that human bias. So we want to know conclusions about a particular population, and this is how we get to it. So we want to know about students in general. We don't want to just know about the students in our class. We want to know, does our treatment help students in general? And we can only get to those students in general by taking a look and basing conclusions on studying a sample, studying some small subsection of the entire population. And I will give you a heads up to introduce this in the textbook. They make a decision to go one way. I don't like it, so we're going to be going a slightly different route in the lectures. They actually teach you how to do this incorrectly at first and then try to correct that error later on. I think that's counterproductive to teach you incorrect first and then try to correct it later on. So anyways, the idea is the same. Conclusions will be based on results for studying a sample. The only difference is that for the time being, your book will use a sample of one individual. It will use a sample of, for example, one student and one student only. That does not happen in psychology. That means that you can use the population distribution to stand in for your distribution of sample means. That's the only reason they do it, but I don't think it's the right move. So just to be aware, in your homework, you will be dealing with one sample of one individual. Don't get freaked out by that. The logic is exactly the same, but we're going to be doing it the right way from the get-go. All right. So what's the core logic? What are we doing here? So in this situation only, to kind of introduce the idea of hypothesis testing, we're going to make an assumption that very rarely ever occurs, and that is that we are starting with a known population. So just to make the introduction of hypothesis testing a little bit easier, we're going to assume that for whatever population we're interested in, we know the mean of that population, and we know the standard deviation of that population. We're going to make that assumption to make it a little bit easier. What we want to know, what our hypothesis is what would happen if we were able to treat that entire population. What would occur to this population if we could treat the whole population? Well, if our treatment was successful, if our treatment did something, then we would change this known population into a treated population, right? We would change it into this new, unknown population. So if our treatment did something, our original population would change into a new population. So if these were depressed individuals, and we had a treatment for depression, we would end up with a new population of not depressed individuals, right? So this is the new population, and notice we don't know what the new population mean is. Because we know that our treatment did something, but we don't know exactly what it did. So we don't know what that new population mean is, and we don't know what that new population standard deviation is either, right? Because again, we don't know what our treatment does exactly to the scores in this population. So it's unlikely and probably unethical to treat an entire population. So how can we test our treatment? Well, we take a sample from this known population. We take a sample of subjects and we treat those subjects and see what our treatment does to the sample. So we treat our sample and then measure that treated sample, and then we decide whether or not our treated sample has changed enough so that it now belongs to that treated population, or did it not change enough so that it still belongs to the known population. If it changed enough so that it belongs to the treated population, we say that our treatment is effective. If it did not change enough so that it still looks like it belongs to the original population, we say that the treatment is ineffective. All right, so that's the core idea. We're looking at this treated sample here, the subjects that we can actually measure. And two final things to mention before we take a look at an example. Number one, we're going to make one more assumption. That standard deviation of the treated population that is unknown, we're going to assume that it's the same as the known population. So we're going to assume that all our treatment does is move our population to a new mean. It doesn't stretch it out and it doesn't squeeze it together. That assumption is just made because it massively simplifies the mathematics. This was before the times of computers when they put this process together. So it just simplifies the math of it. The other thing we're going to assume, and this seems rather counterintuitive and foolish, and it actually is, we're going to assume that we did not measure our sample before we treated it. All right, so this again just kind of simplifies the introduction of hypothesis testing. We're going to assume that we forgot to measure our sample before our treatment. Right? So usually when you give people a treatment, if you're treating their depression, you measure their depression before the treatment, and you measure their depression after the treatment, and then you compare the two. To simplify things, we're going to assume we forgot to measure them before the treatment. So that'll come in later, but just for now, we're assuming that we forgot to measure them. All right, so the hypothesis testing process. 5 steps that are going to allow us to study any single population, test any single hypothesis. Here are the 5 steps. We'll go through them one by one. Step number 1, restate the question as a research hypothesis and a null hypothesis about the population. Notice, about the population, not about the sample. Step 2, determine the characteristics of the comparison distribution. Step 3, determine the cutoff sample score on the comparison distribution against which the null hypothesis is going to be accepted or rejected. Step 3, determine your sample score on the comparison distribution. And then finally, step 5, decide whether to reject or accept the null hypothesis. So those are the 5 steps in general. So let's take a look at each of those specifically. Step number 1, restate the question as a research hypothesis and a null hypothesis about the population. All right, so in general, what we want to know is whether or not there's a difference between the treated population and the untreated population. If there is a difference between your treated and your untreated populations, that means your treatment did something. If there is no difference between those two, that means your treatment did nothing. So that is how we can tell whether our treatment is effective or not. This is an English sentence that cannot be tested in statistics. First thing we need to do is we need to translate this question into something statistics can actually analyze. We need to translate it into a null hypothesis and a research hypothesis. The research hypothesis. The research hypothesis can be stated as, or the idea behind the research hypothesis is that your treatment has an effect. Your treatment does something, right? Your treatment makes a difference, right? That is the research hypothesis, that your treatment does something. That is written as this: the mean of your treated population does not equal the mean of your untreated population. So let's say that you have a treatment and you have, let's get this over here. Let's say that you have a magic IQ pill, right? So you got a pill that you suspect or you want to test whether or not this pill can increase or change a person's IQ. So let's say that the population, the untreated population, has an IQ of 100, right? That's what the untreated population has. You give the entire population this pill, and your treated population has an IQ of 115. Your treated population does not equal your original population. Your IQ pill works. It's increased everybody's IQ by 15 points. All right, so that means that your treatment makes a difference. Let's take a look at the other scenario. Mean of the untreated population is 100. Let's say that you give everybody your IQ pill. IQs go down to a mean of 85. Your original mean does not equal your treated population mean. Your IQ pill is effective. It's horribly effective. It's effective in the wrong direction, but it works. It does something. It has an effect. So when the treated mean does not equal the original population's mean, the untreated one, that's when your treatment has an effect. So that's the research hypothesis. The other one that we need is the null hypothesis. The null hypothesis is that your treatment does nothing, right? Your treatment has no effect. And this is written as the mean of your treated population equals the mean of your untreated population. So if I had a pill and the original population had an IQ of 100, and I gave everybody my IQ pill, and after the treatment, the mean IQ of the population was also 100. My pill does nothing. It doesn't change IQ whatsoever. My pill is ineffective. My treatment has no effect. So that's the research and the null hypothesis. And notice that for the research and the null hypothesis, all three possibilities will be covered. So the null hypothesis, the null hypothesis covers the possibility that there's no change. And in this case, the research hypothesis covers the possibility that maybe your treatment increases the scores, or maybe your treatment decreases the scores. So that does not equal, covers increases and decreases. So we got every single possibility covered for the research and the null hypothesis. All right, step 2, determine the characteristics of your comparison distribution. We need to compare our sample's score to something, and your comparison distribution has to be something that you can compare a sample mean to. So it has to be something where we can represent the population distribution if that null hypothesis is true. You cannot compare your sample mean to a population distribution because you're comparing a score of a group of people to scores of individuals. And that's not fair. You can't compare the performance of a group to the performance of individuals. It would be like playing a basketball game where you have one full team on one side and one single person on the other side. You take a look at that and say, that's not a fair game. Same thing with stats. We can't compare the scores of a sample to scores of individuals. We need a new distribution, a distribution where we can compare our sample mean. And that new distribution that represents your population distribution that new distribution that is made up of sample means, so that it's fair to compare your sample mean to a distribution made up of sample means, that's that distribution of sample means. So that's why we did that last part of chapter 4. That's why the central limit theorem is so important. And this is why we can use that normal distribution, because we are comparing our sample in our experiment to a distribution of sample means. We might not know what the population looks like, but we surely do know what that distribution of sample means looks like. It looks like a normal distribution. So this comparison, this characteristics of the comparison distribution, this is where our normal curve, our distribution of sample means, is going to come into play. All right, step number 3, set a cutoff sample score or a critical value. This is your line in the sand. This is the target where you are going to compare your study to. So remember that we have this distribution of sample means. And we got a whole bunch of means that came from this population. What we're going to do is we're going to identify which means are just too unlikely for us to believe that they occurred by chance. Right? So we're going to draw a line in the sand. And we're going to say to ourselves, here's our line, here's our critical level. And even though means on this side are possible in our population, we're going to say that they are just way too unlikely for us to believe that they occurred. Right? It's just way too unlikely. It's kind of like, this is a line in the sand, kind of like when you hear excuses from an individual. And how far are you willing to go before you say, I don't believe you anymore? So let's say that you asked a friend of yours to help you move. Right? Let's say that you're like, oh yeah, come by on Saturday. We'll start at 9 a.m. And I could really appreciate your help. And they're like, yeah, sure, I'll be there at 9 a.m. On Saturday, they show up at 3 p.m. And you start asking them, well, what happened? Why didn't you show up at 9 a.m.? And they might say things like, oh, well, my car broke down. My engine wouldn't start on. That's excuse number 1. And you're like, oh, okay, well, that's unfortunate that your car couldn't break down. And then they're like, yeah, and my internet was gone, so I couldn't call a cab. That's excuse number 2. And you're like, okay, well, seems less likely, but, I'm still willing to believe you. Oh, and my wife went into labor, so I had to go to the hospital. That's excuse number 3. Well, the hospital was full, so we had to drive to Indianapolis. Excuse number 4. But then when we got there, there was a 2-day waiting time, right? Eventually, all those excuses are going to pile up, and you're going to say, you know what, it's possible. It's possible that all these things happen, but it's so unlikely. You've crossed that line of believability. You've crossed that line in the sand. I don't believe you anymore. I'm throwing out your entire story. That's what that line is right there. Even though these samples are possible, they're so unlikely that we're going to assume that if our sample ends up over here, it's actually because our treatment pushed it into this edge, pushed it into this tail, rather than we just happen to have this really unlikely sample. All right, so step 4, once we determine our cutoff score, once we determine this line in the sand, that is just, no, that's not better. Once we determine that line in the sand that is just so unbelievable that we reject its possibility, once we determine that line, next we have to determine where our sample actually is. So we calculate where our sample is on this distribution, and we do that by using the unit normal distribution table, that table we've been working with in chapter 4. And then, depending upon whether our sample crosses this line and goes into the tails, or whether it stays here in the body, we make our final decision. And if you compare your sample score to this critical cutoff score, and your sample score is beyond the cutoff score, your mean ends up here in the tail, that means that your treatment pushed your mean into this tail, and we accept the research hypothesis. We say our treatment is effective. We reject the null hypothesis, reject the idea that our treatment does nothing. So we accept the research hypothesis, our treatment does something. Logically, we have to reject the null hypothesis, the idea that our treatment does nothing. However, if our sample score is within the cutoff score, if it's within the body over here, well then we say, all right, we believe you, we believe that you're still part of that known population, and we accept the null hypothesis, we say that our treatment hasn't done anything, and we reject the research hypothesis, we reject the idea that our treatment does something. So you'll notice that whatever our decision is, we will always accept one hypothesis and reject the other. All right, so that's a 5-step procedure. In the general case, let's apply it to something specific. Let's go back to this school. So you go into this school as a child psychologist. They want you to increase the self-esteem of their students. You notice that their students are doing nothing but endless push-ups in their physical education classes, and you think that that might be the reason why their self-esteem is low. So you take a selection of students, you take a sample of students, and you give them this treatment that you've developed, this games program designed to raise the self-esteem of students. You give them that program, you put them through that treatment, you measure their self-esteem after the treatment, and then you want to know, is the self-esteem of the population of students who do this program, if you apply this program to the population of students, will the population increase their self-esteem above the levels that the population has now? Or, on the other hand, did you just get a fluky sample that started with high self-esteem? Did you just end up with the highest self-esteem children in the school just by chance? So if we want to answer something about the population of students in schools in America, we need to go from our sample and do a hypothesis test to see if it applies to that population. All right, so let's set this up. Here's the description of the situation. I'll read this out for you. So it goes, a researcher is evaluating the effectiveness of a new physical education program, the GAMES program, for elementary school children. The program is designed to reduce competition and increase individual self-esteem. A sample of 16 children, so we take 16 children from the school, is selected and children are placed in the new program. After 3 months, each child is given a standardized self-esteem test. So notice, we're just making the assumption we didn't measure their self-esteem at the beginning. Typically you would, but this is just to illustrate hypothesis testing. So, we don't measure their self-esteem at the beginning. After 3 months, each child is given a standardized self-esteem test. For the general population of elementary school children, the scores on that self-esteem test form a normal distribution with a mean of 40 and a standard deviation of 8. So because we're using a standardized test, we actually know the population distribution. That test has a population mean of 40 and a population standard deviation of 8. So if our sample mean is 43.5, so those 16 students, we gave them the standardized self-esteem test and they scored 43.5. That's your score on this standardized test. If the only thing we were interested in is whether or not our treatment program worked for those 16 students, we could just stop right there. And we could say, you know what? Those 16 students, 43.5, that's their score, that's their average score. That's higher than 40. So our games program worked for those 16 students. But we don't care, well, we care about that, but we care about more than that. We want to know, does it work for the population of students? So based on this 43.5 score for our sample, is this enough to demonstrate a significant effect? We're going to assume a two-tailed test with an alpha of 0.05, and I'll explain what all that means in just a moment. So we're doing a hypothesis test. That's our situation. Let's get down to business. So we got our 5 steps that we're going to go through. Let's start off with step number 1. We need to restate the question that we're interested in as a null hypothesis and a research hypothesis about the population. This is what we want to know. Is there a difference between the game program students population and the general untreated student population? So if we were able to apply our games program to all the students in the United States, will that change the population of students? That's what we want to know. This English sentence cannot be tested statistically. We translate it into a research hypothesis. The research hypothesis is that the games do have an effect. Our games program does change self-esteem. And we write that by saying that the mean self-esteem for the games program population does not equal the mean self-esteem for the general population. If the mean of the self-esteem for the games population does not equal the general population, that means that our treatment did something. It's changed things. It's changed the mean. On the other hand, the null hypothesis is that the treatment has no effect. Our games program is no good at increasing self-esteem. It does nothing. In that case, if we applied it to the population, the mean self-esteem of the game students would be the same as the mean self-esteem for the general students. The scores would be the same, self-esteem would be the same. Our treatment does nothing. Our treatment does not change self-esteem at all. So that's what we're trying to decide between. Do we accept the research hypothesis? Our treatment does something? Or do we accept the null hypothesis? Our treatment does nothing? We'll know by the end of our 5-step procedure. All right, step 2, determine the characteristics of the comparison distribution. All I want you to think about right now is that your comparison distribution is not your population distribution. It is your distribution of sample means. And the only time your distribution of sample means will look like your population distribution is when you have a sample size of 1. That's why in your homework you will start off with a sample size of 1. But as soon as you add more and more people to your sample, your distribution, your comparison distribution, starts looking like a normal curve. Importantly, does not look at all like your population distribution. So we need to determine the characteristics of the comparison distribution. We're going to see how to do that in chapter 6. For right now, I'll give it to you. And it just so happens that our comparison distribution has a mean of 40 and a standard deviation of 2. So this distribution of sample means that is made up of all these different samples, it has a mean of 40, right? So that distribution of sample means has a mean of 40, same as the general population, and it's got a standard deviation of 2. All right, so that's our comparison distribution. Next thing we want to do is we want to set a cutoff sample score or critical value. And this is the target, right? This is the line in the sand that we draw, where we say to our sample mean, if you cross that line, if you go over into this tail, we're going to accept that research hypothesis, we will. But if you stay on this side, we'll accept the null hypothesis. It's our line in the sand. We'll see how to do this very soon, but for right now it has to be given to you. And it is a z-critical z-score of 1 plus or minus 1.96. So what we see here is that we're dealing with z-scores. The reason is because we need a table for our comparison distribution. We need a table that we can use to look up our comparison distribution. And nowhere in the world is there a distribution of sample means for a mean of 40 and a standard deviation of 2. There's no textbook that has a table for this. So what we do is we change this into a distribution of means that got transformed into z-scores. So for our z-scores, we have a mean of 0, we got a standard deviation of 1, and we have a critical score of plus 1.96. This is going to be if our treatment increases our scores. We also have a z-score of minus 1.96. This is our cutoff score or our critical value if our treatment decreases the scores. So those are the two lines in the sand, and we need to find out where our sample is on this distribution. So notice this move. We're still dealing with this distribution of sample means, but so we can access it, we've changed it into a distribution of z-scores.
Do people ever set a research hypothesis where it's like just a positive effect or just
Yes.
Yes.
Yep. So there's two major types of research hypotheses. There's this one called two-tailed, where you're just looking for a difference. And then there's ones like you described, which are one-tailed, where you basically say, well, we're not interested in this side. And then we only have one tail. So we'll get to those. That's like kind of like the next step once we introduce this. It's a good question though. Because honestly, this makes no sense. This side over here. Why would you care if your treatment program crushes the self-esteem of these children, right? We're not interested in that. But just at this point, we'll keep it as a two-tail. All right, so those are our critical scores. We'll see how to do this soon. But just for now, be aware, we have these cutoff scores, right? Those are the lines in the sand. And we need to find out now, where's our sample on them? So we know that our sample in the original distribution of sample means is somewhere over here, right? Because that's a mean of 40. Our sample has a mean of 43.5. So we know that it's somewhere over here, but we need to find exactly where it is. We don't have a table of this, so we need to find where our sample mean is over here. We need to find the z-score for our sample mean. So to do that, we go to our sample mean. It was a score of 43.5. We go to our comparison distributions parameters, mean of 40, standard deviation of 2, and we calculate the z-score using our formula for z-scores, and we find out that we have a z-score of 1.75. So we don't know where exactly on this distribution our sample is, but we know on our z-score distribution, we have a z-score of 1.75. That's 0 right there. That's 1.96 right there. That's where our students are. That's where the mean is, that z-score of 1.75. 43.5 over here got changed into a z-score of 1.75. That's about where it is on our comparison distribution. So, step 5, decide whether to accept or reject a null hypothesis. If the sample z-score is beyond the cutoff z-score, it's not, right? Our sample z-score did not make it beyond that line. It didn't cross that line. If it did, we would accept the research hypothesis. We would say, great, our treatment works. And we would reject the null hypothesis. However, we are in this situation where our sample score is within the cutoff scores. It's in the body over here. It didn't make it to the tail. It didn't cross that line. In this case, we accept the null hypothesis and we reject the research hypothesis. So for this situation, we would accept the null hypothesis and we would conclude that our games program doesn't actually increase self-esteem. It doesn't actually change the self-esteem of students. Our games program made no difference whatsoever in the self-esteem of the population of students. So we just had students that were higher in self-esteem because we just got unlucky and happened to choose students randomly who were higher in self-esteem, but not high enough where it's unbelievable. All right, any questions on that so far? Okay, so we're going to do one more example here, and this is to show you two things. Number one, this 5-step procedure, there's a logic behind it. And I've been pointing out the logic behind it. I've been explaining a little bit about, is this sample really unlikely? Or was this sample, that high because of the treatment? So that's something that that's one of your end goals. That's one of the things that you want to get to eventually. However, an understanding of why hypothesis testing works is not required in order to do hypothesis testing. So if you are sitting there and you're still a little bit confused, it takes a little bit of time for this idea to sink in. It takes a little bit of time before it kind of snaps together in your mind. If you're at the point where you're like, you know what, I don't really understand it, I don't really get what this hypothesis testing is about, that is fine, that's okay. You can still do hypothesis testing by just following the 5 procedures, right? It's kind of like baking a cake. You might not know why a cake rises. You might not know why you have to pour in your dry ingredients first and then your wet ingredients. You might not know why you're doing that, but you can follow a recipe and end up with a delicious cake. Same thing with hypothesis testing. You might not understand the underlying logic yet, but you can definitely go through those 5 steps and come to the correct conclusion. So that's the first thing we're going to illustrate with this next example. The second thing we're going to illustrate is why we need an objective procedure for making these conclusions. Because let's say we have the exact same situation, right? The exact same students, exact same treatment, exact same school. And let's say that after we ran our initial study and we say to ourselves, you know what? Our treatment does not increase the self-esteem of students. Well, there goes those years of research, and there goes that great idea. I guess we're back to the drawing board. I guess we throw out all of our developed materials and we got to start from scratch again because this experiment has shown that our treatment is not effective. Let's say that during that pity party, one of your research assistants runs in and says, oh my gosh, oh my gosh, oh my gosh, I am so sorry, I scored the self-esteem questionnaires wrong. I didn't even notice that I did this. What I did is I forgot to add 1 to every single score. I was supposed to add 1, I forgot to add 1. I'm really sorry. It turns out that the mean score for these students is not 43.5, it's actually 44.5. Right? The mean score is actually 44.5 instead of 43.5. To our human minds right now, me looking at this, I would say, well, we missed at 43.5, we're going to miss at 44.5. Why would 1 extra point make any difference, right? To our human minds, it's like, that's not enough of a difference. It's kind of like somebody saying, to you that, oh man, I did really poorly on my test. I got an 88. And you're like, well, what score would you have been happy with? Oh, I really wanted an 89. 88, I'm over here, I'm super sad. 89, I'm over here, I'm ecstatic, I'm over the moon. You're like, it's just 1%, it's just 1. What's the difference? That's our human mind talking. We're going to see why we have this procedure right now. So let's redo this procedure, this time with the correct score, right? This time with the real score. So the nice thing about this is that most of this procedure is not going to change because we've already done, most of it is going to stay exactly the same. So step number 1, restate the question as a research and a null hypothesis about a population. That doesn't change. We're still interested in whether or not there's a difference between the games program and the general student untreated population. We still have a research hypothesis that says that our games do have an effect. So the mean self-esteem of the population that does the games program will not equal the mean self-esteem of the population of general individuals. Maybe they'll be higher, maybe they'll be lower. Research hypothesis says they will just not be the same. Null hypothesis stays the same. The treatment has no effect. The mean of our games population will be the same as the mean self-esteem for our general population. Our treatment does nothing. So that stayed the same. Determine the characteristics of the comparison distribution, not the population distribution. Your comparison distribution is your population distribution only for a sample size of 1. We got 16, which means that we are dealing with a distribution of sample means. So we're going to determine the characteristics of those distributions. We're still going to find out how to do that next chapter. I'm still going to give it to you right now. It has not changed. Right? So far so good. We haven't had to change anything to update our hypothesis test. What next? Set a cutoff score or critical value. Set your lines in the sand. We're going to see how to do this very, very soon, but it also has not changed. Our lines in the sand, our critical scores, are still minus 1.96 and plus 1.96. Those still are the critical values. So what has changed? Well, step 4 has changed. Because we need to determine where our sample score is on our comparison distribution. Where is our sample in this comparison distribution? Well, we know that it's 44.5 now. So we know it's moved. So we need to find out where it is. We can't do it for this distribution we got to transform it into z-scores, so we can look at it in this distribution, this transform distribution. We got a mean of 44.5, standard deviation of 40, mean of 40 for the distribution of sample means, standard deviation of 2, sample mean of 44.5. We calculate our z-score, and we end up with a z-score of 2.25. So what that means is that our mean used to be here when it had a z-score of 1.75. But now, that's 0 right there. That's 1.96 right there. 2.25 is somewhere in there. 2.25 is somewhere in the tail. Importantly, 2.25 is in the tail. We have crossed that line. Our treatment has pushed these students, this mean, into this highly, highly, highly unlikely zone. So once it crosses into that unlikely zone, you're in that situation you were with your friend when they moved, when they said they would help you move. Either you believe every single excuse compounded on top of each other, or you say, you know what, that's so unlikely, I'm rejecting your excuses, I'm saying our treatment works. That's what we're doing here in step 5. So if the sample z-score is beyond the cutoff z-score, it is. Our sample went beyond, out of the body into the tail. Now we accept the research hypothesis and we reject the null hypothesis. If, on the other hand, we were in the same situation we were before, if our sample was still in the body over here, then we would accept the null hypothesis and reject the research hypothesis. As it turns out, we have crossed that line, so we reject the null hypothesis, we accept the research hypothesis, and we conclude that our games program does change the self-esteem of students compared to the general population of students. And now we get on the phone, and now we call up every single school, and we say, you know what, are your students low in self-esteem? Well, boy howdy, do I have a program for you. Let's meet to discuss your physical education program. And notice that this difference, this change in our conclusions came from a difference in the score of 1, right? 43.5 being the average, our program doesn't work. 44.5 being the average, our program does work. And human minds are horrible at finding where that line is. That's why we need these objective measures. That's why we need this systematic procedure for hypothesis testing. And that's what opens up our ability to help not just our 16 students in our experiment, but now the population of students across the United States. All right, so that's the beginning of hypothesis testing. We're going to take a break right now. Let that sink in. Let that kind of, get into your mind here. We're going to take another 15-minute break before we come back and take a look at some more hypothesis testing. But this is going to be it for the remainder of the semester. We're going to be doing hypothesis testing for the remainder of the semester. The only thing that we're going to do is we're going to learn different versions that work for different situations. But this is basically it. So keep trying to understand the logic of hypothesis testing. What is it doing? What are we actually trying to determine? But also take comfort in the fact that even if you do not know what's going on under the, behind the curtain, as long as you can follow those 5 steps, you can do hypothesis testing every single time and come to the correct conclusion. All right, so that is what I wanted to cover for this second half. So it's 11:05. We'll take a 15-minute break. We'll come back at 11:20 and continue on with today's class.